Hello and welcome to the Oxford MAT Livestream. My name's James and you've joined us today for some integration and differentiation. And this time with chat on screen, hopefully. Good to be here, good to see you again. I am going to quickly say hi to chat, who I can see Urban and some anonymous people. And people have noticed that they might be doing the same exams as each other at the moment, so that's exciting. But in a second, I want to get going with the question sheet. If it's your first time watching the Oxford MAT livestream, we've got a question sheet. I think I call it a worksheet sometimes. It's got a bunch of revision material and questions, and then some math questions as well. Hi to Miles and an anonymous person. There you go. And chat live updates. There we go. On the screen at last. That's not going to be there for the whole thing. I'm going to turn it on and off. Somebody showed me some more technology, so that was pretty good. Hi, Will. Right, okay, now you can see who I'm talking to, for the bits where I'm talking to someone. The technology. For example, Zoe joins. I can say hi to Zoe. And there's a little bit of lag. There's a bit of weird lag, but we can work with that. Last week I told you I'd try and get ahead of schedule by posting those worksheets to the website. That did not happen. Things got worse. So this one was only published today. If you're watching the replay, you're probably unaware of this ongoing battle for me to try and get ahead of myself. But hey, hi to Michael and A and some other people. Someone says nice haircut. Cheers. I've lost a lot of hair. Emmanuel says it's their first time watching live from the building. And an anonymous person wants to know. Hi Daniel. An anonymous person says, yeah, how long before the live stream? I posted this one this morning. That's a bit later than I wanted to. I would like to post them at least the day before. I'm aware that I'm saying these things into the camera. They'll be recorded on the internet, and then everyone will know that I'm locked in this battle to try and get ahead of myself that has not really come through so far. Right, good. So I'm starting math revision today. A perfect time to start. Whenever you start, it's perfect time to start. I love doing math revision, and I always tell people that they can use this if you're thinking about maths, then you're already doing math revision. So even if you think you've only started today, this is probably not the first time you've seen any maths. Let's do this poll at the start for how's your day been so far. People are welcome to vote for anything between 1 and 5 stars inclusive. That's a whole number. While they're doing that, I'm gonna say what I've got on the screen. So the MAT syllabus, the amount of maths that we think you know by the time that you maybe sit the maths admissions test, is pretty limited in terms of integration and differentiation. I've put on the screen, I think, everything that you should be able to differentiate for the maths admissions test. I'll walk through them. 2 of them are a bit vague at the bottom there, but 2 are very specific. Those first, look at that graph. The first 2 are powers of x and exponentials, x to the a and e to the kx, where a and k are both constants. Would like you to be able to differentiate those. If you've never had to differentiate those before, then put the formula on the right hand side. If you've never heard of differentiation before, it's a formula for what the gradient is. The gradient in terms of x on the right hand side there. You might have met the gradient of a straight line, that's just some number, but the gradient of a curve depends on x. It's different steepness in different places. So here on the right is function of x, and this is something at A level people just learn these functions of x and that relationship that's something like take the power, bring it down the front, subtract 1 from the power for powers of x, and for exponentials, and always take that k constant up there, put it in the front, but keep all of the exponential stuff, don't subtract 1. And people learn these as kind of rote rules. At university, if you do a maths degree, you learn some reasons for why these are true. It's odd, really. There's not really a nice. It's not obvious that there should be a nice formula at all, right? If I show you a cubic graph and say, the gradient's different things in different places, the formula for that, maybe it's surprising that it's a quadratic. I don't know. Sometimes it's hard to find these things surprising once you've learnt them, but in some sense it is still surprising. Quick look at chat. Nikita has noticed that chat's not anonymous. You've always been able to stick your name somewhere in the chat thing if you want to. Okay, and people have voted there for about 4 stars, which feels like about the average. A few people voting 1 star and 2 star, always looking out for you. However bad it's been, at least you didn't have to have a haircut. Right, probably. I hope you didn't. That doesn't land very well if you did. I can't work out how to switch that off. There we go. Right, chat. Is the worksheet link in the description not working for anybody else? That's entirely possible. I'm going to try and live edit it. Wish me luck. While I'm doing that, why don't you tell me in chat, what other stuff do you personally know how to differentiate? Not on MAT, this is it for MAT, but what other stuff do you know how to differentiate? Stuff where you know a nice formula for what's going on. It's not just you, that link is not good. Someone in chat can differentiate a to the x, that's pretty good. A to the x where a is a constant. I kind of reckon if you know about exponentials, then you can maybe make that work. Is the entire Oxford Maths website down? That'd be fun, wouldn't it? Yeah, I think maybe the entire Maths Oxford website is down. Or maybe I've got no internet and this isn't really happening. No, I think the entire Maths Oxford website is currently down. Okay, if you're watching the replay, then hopefully you can get a copy of the sheets. Otherwise, I'm going to put them on the screen. People in chat have learned how to differentiate logarithms and trigonometric functions. Yeah, those are probably the next ones you learn at some point in A level. I can't remember when, but that's fair enough. Products and quotients. Yeah, chain rules. Inverse, tan. Oh, right, okay. People have differentiated a bunch of stuff. Yep, I think the whole maths website is down. We're going to... Sorry. Luckily, we broadcast this separate from the maths website. Products of things. Yeah, okay. Maybe it's back. Okay, right. Wanted to point at the last 2 lines of this screen as well. I've realised that I sort of skipped them. We expect you to be able to differentiate sums of functions. That's easy, really. It's just the sum of the 2 derivatives. So here I've got y1 and y2. If you see them added together, you're supposed to add together the derivatives. That's good combined with the first one because those let you do, well, sums of powers of x. Combined with this last one as well, if there's a constant out the front, then that's just a constant. It makes everything steeper, but it does that everywhere. Constant out the front. Never sure if thinking about gradients is actually helpful or not. It's one of those things that's very algebraic when you're actually doing it, so you might as well just start doing things. Sums of derivatives, sure. So you know how to differentiate x to the a. So if I give you x cubed, you know how to differentiate that. If I give you e to the x, you know how to differentiate that. If I give you the sum of those functions, x cubed plus e to the x, which is, oh gosh, something like this. Woo. Oh no, too much. X cubed plus e to the x is going to be something like that, really fast upwards. Okay, its gradient, the y over the x, it is a function of x. It's 3x squared plus e to the x, which, once you've worked it out, you realise, aha, that's always positive. In fact, it's not 0 anywhere, because x squared is positive and e to the x is always positive. So my first picture was rubbish because I drew it going down and it actually just keeps going up. Faster and faster and faster because e to the x gets larger. So this kind of way of finding this derivative might give you information about whether the function is increasing or decreasing. Good stuff. Okay, thank you for asking for an example. I think that went semi-well. Okay. Basil has joined and says it's working. Is there a question bank for maths that's not in the official Oxford MAT page? We've gone back to 2007 on the official Oxford MAT page. That's quite a lot of questions. And other people are differentiating functions. Question bank, what more do you need? So there was a MAT-like test, I think also called the MAT, confusingly, before 2007 with a different format. And if you go back far enough, it's a completely different test. At one point it was two examples. Is it the derivative of e to the x is x to the x? No, so the derivative of e to the x for exponentials, where e is the number 2.7-ish, this weird constant. It's got this amazing property that the derivative is, you bring down the constant from up here. So e to the x is like e to the 1x. I see. So you have to imagine there's a constant k in here, that's the number 1. Oh, I'm writing exactly underneath chat. It's a new danger. Right. E to the x is e to the 1x. So using this rule over here, that would become 1 times e to the 1x. Okay. I agree that's confusing. I haven't defined that very well, perhaps. I haven't explained it very well at all. If you're learning about exponential differentiation today, I should probably have told you that fact first. E to the x is amazing. Its derivative is e to the x. And other ones we can work out. And what's your favourite approximation for e and pi? They are both about 3. E plus pi. Oh, that's really close to 6, right? Good. Okay. Taking Matt outside the UK, we're going to put some advice on our website hopefully next week before the big university open days. So for quite a while now I've been saying check the website in the future. I've now got a vague date. We've been doing the Matt outside the UK for years and years, so hopefully going to keep doing it. Otherwise, yeah. Right, okay. I'm going to switch off chat, I think. Well, I mean, chat's going to keep running, but not on screen because I want to show you the questions. Because I think some people, maybe me included, can't get to the website right now, so we're going to rely on this. Okay? Yeah, let's do it. So I've copied out the MAT syllabus. We've done this a couple of weeks now with just a couple of short lines from the MAT syllabus. And this one, more stuff fell under integration and differentiation, so I'll put all of it. That bit there at the top is explaining what we expect you to be able to differentiate, and the sum of functions as well. There's some stuff about tangents and normals to the graph. Once you can find the gradient, you can do some sort of geometry stuff with that, so that's good. Turning points, second order derivatives sound much more scary than they are. Maxima and minima, increasing and decreasing functions. Oh my goodness, there's all things you can do once you know what the gradient of a function is. Differentiation from first principles, I'm just going to say a tiny bit about. And then integration. Generally, I expect people to be able to integrate anything they can differentiate. Sorry. Wait, no. Integrate anything that comes from doing some differentiation. Reverse, put it back to what you had before. I think that factors in there somewhere. Yes. Indefinite integration as the reverse of differentiation. Right. That run through the MAT syllabus should hopefully be either familiar topics you've heard of or stuff we're about to learn about or realise it's the same thing with a different name. Uncompleting the triangle. So I'm going to go through some revision notes quite quickly. Again, this is probably not the best way to learn about differentiation or integration. I'm not even a qualified maths teacher, right? So if you have access to a qualified maths teacher, or maybe armed with these revision notes if you don't, it's maybe worth learning this material in a not live stream format. But having said that, here we go. So we've got sums of derivatives in there in the middle. It's one of those things that when I type it out in the revision notes, the sum of the derivative of y1 plus y2, it feels really silly because it's just differentiation respects the plus sign. Thing plus thing, derivative, thing plus thing. So I had to put an example in of something where it doesn't do that to convince you that it's not always so straightforward. It's not the case that the square of x plus y is the square of the first thing plus the square of the second thing. You might like to think of 2 more examples. I guess this is for people who've already seen this stuff and need something else to think about. I'd like 2 more examples. One, which is like differentiation, where if you have x plus y, thing 1 plus thing 2, and you do whatever you're thinking of to that object, then that's the same thing as doing it just the first one plus doing it just the second one. Like how for differentiation, the derivative of y1 plus y2 is the derivative of y1 plus the derivative of y2. So differentiate them separately and add. Yeah, this property is called linearity. So, boring version of this question, please give me another example of a linear operator. And the other example I'd like is something that's not a linear operator, or said properly, something for which you can't always just apply the thing to each object and then add them together. Yeah, expected values are good because in probability, if you've got 2 random variables, x1 and x2, the expectation of the sum of those variables is the sum of the expectations. That's a good example from some sort of totally different, right? Somewhere totally different expectation of a random variable is kind of nothing like differentiating a function, but they kind of behave in this similar way. Leo's brought in complex numbers. Is it correct? I'm not sure it is. I'm going to look really closely, but I don't want to talk about complex numbers too much. Let's put chat on screen. Can't see what chat's talking about. Inversion is not a linear operator. What's the difference between derivatives and differentials? I'm going to be very vague with the language today. In particular, I'm going to say derivative almost all the time. And if I say something else, it's probably a mistake. Multiplication. Right. Yeah, so multiplication, you've got to be a little bit careful with what you're talking about. But it's definitely true that A times brackets B plus C is the same thing as A times B plus A times C. Maybe that's what you mean, that it's got this linear property. Maybe you mean that A times... Yeah, respecting the plus sign. I've got to be careful about where you're putting the math sign. Right. I turned on chat, but then didn't actually turn it on. That was very embarrassing. Turns out if I switch it on, it only goes to the preview. Let's fix that. There we go. Okay, good. And now I've got more space. Yeah, good stuff. Inversion's not... Yeah, okay, good. Right. I was doing revision. We're doing revision. There we go. So tangents and normals are worth talking about. I'll do it in terms of geometry first. The tangent is supposed to have the same derivative at a particular point, the same gradient at a particular point as your curve. So if I have a curve and I want the tangent at that point, they're supposed to have the same derivative and the same value. So that line, in a way, that line becomes like a good approximation to the curve nearby. You don't have to think of it like that, but it means that as well as having the right value, the slope's right at that point. So it's kind of the best you can do with a line mimicking your curve at that point. The line, you've got two things you can change: the value and the constant on your line, and the gradient of your line. If you choose both of those so that it matches up the value and the derivative with your curve at that point, that's probably the best you can do. I switched chat off again because I wanted to talk about the thing behind. I need more boxes, right? I need more boxes. Good times. People in chat are arguing about complex numbers, so maybe it's also helpful to switch off chat for this while chat's talking about complex numbers. Okay, the normal geometrically is just at right angles to the tangent. So finding the normal at a point, people normally find the tangent first, or at least find the gradient for the tangent first, and then write down the gradient of the normal. There's this fact that I think we mentioned last time, that the gradients of two lines multiplied to -1 if the lines are at right angles. It's a really good fact. How do you know if you can differentiate a function? Says an anonymous person in the chat. It's a good question. I think at A-level you learn particular functions. This is a terrible answer, but at A-level you learn particular functions that you can differentiate, and that's about it. Nobody gives you this general rule about what it would mean, except I suppose you get a hint of differentiation from first principles, which we'll talk about in a moment. At university, if you study maths at university, you learn a lot more about what it means to be able to differentiate a function. And this differentiation from first principles becomes sort of the main way that you think about differentiation. But for us on maths, without getting sidetracked, we're going to focus on polynomials, exponentials, sums and multiples of functions. Okay, I've got an example of finding a normal there using the -1 trick. So turning points. In general, you look for turning points by setting the derivative to 0. If you imagine a turning point like on a quadratic at the top, a turning point will be where the function is neither going up nor down, so it's got 0 derivative. It's technically necessary but not sufficient that you've got to check what your function is actually doing there, which is a little bit painful, but means that technically you're looking for stationary points when you set the derivative equal to 0. But a normal thing to do would be like check what's going on. There are some weird examples, and you can make weirder examples than x cubed. Okay. Second derivatives work by doing the derivative twice. Examples for power of x there and an exponential. And maxima like on unhappy quadratic, minima like on a happy quadratic. Okay. Although I guess in that sentence I've used the plural. There's a little Latin lesson on here as well. Okay. I've been slightly distracted by chat. Chat's asked me to prove geometrically the fact about gradients, which somebody asked last week as well, and it's very tempting to get distracted. So I'm going to set it as homework. Let's do the setup. I'll meet you halfway, because chat seems very interested in this. We'll put our revision notes at the top of the screen. Revision notes at the top of the screen, and we'll put some stuff about gradients at the bottom. And we're just going to get distracted for a little bit. Okay. Here's how you would work it out. Set up your triangles. Set up some triangles like this. So that you've got two lines. These are my two lines. Oh, that was way too steep for this picture. I've got two lines. This steeper one here, I'm going to say that's got gradient m1. And I'm going to say this less steep one has got gradient m2. This is 1 over here. Do a whole bunch of angles and stuff to work out an expression for this angle here. That's homework. It's too hard for math, so we're on a sidetrack, we're on a tangent at the moment. Pun intended, probably. So if you do a bunch of angle chasing and write down a fact about tan θ1 minus θ2 or something, then you can get a formula that relates together the gradients m1 and m2 to that angle in between. And if you set the angle to 90 degrees, they're right angles. But there's a more general formula in there as well. Gosh, that's a lot of work actually, that trigonometry problem. Too hard for me. Okay, that was the sidetrack bit there. Quick look at chat, because there's a comment here, some AS level maths topics, like the chain rule. That's because some people are still learning AS maths at the point when they do. No, that's not true. So we'll put pure A2 and pure 2 AS level maths. Yeah, so some things like chain rule and product rule, I think people learn too late for it to be on the mat. I have to remember that some people are learning math in a different order to other people, so that's a whole thing. Yeah. Anyway, the syllabus is what it is. It was at the top of the screen a minute ago. Luckily, we don't have to look up what the syllabus is. Maybe I'm wrong, and I could be asking questions about the chain rule, but too late now. Haven't put the chain rule on the syllabus, so no chain rule questions. Chat's gone. Here's the first principles thing, which is on screen. It uses the idea that the tangent is supposed to have the gradient at that point. Now, what does it mean for a gradient at that point? Because at that point, you can't do a gradient at all, right? For a gradient, you need 2 points, so that you can find the gradient of the straight line between them. So what would it mean to do a gradient at a point? And one way to understand what it would mean to do a gradient at a point is to take 2 points, fix one of them where you want it to be, and bring the other one in along the curve towards that fixed point that you have on your curve. When they get really close, that's a bit like having put 2 points in the same place, 1 point derivative at point. But along the way, you can work out the gradient because you've got 2 points. So you can use your difference in y's divided by the difference of x's to work out the gradient there. Differentiation from first principles says that for the functions we're talking about, you can do that and you get that chord, which is the word for a line between 2 points on your curve. That chord gets closer and closer to being the tangent. I would not expect a precise description of limits or anything. I'd expect people to just have some idea that if I have a fixed point on my curve and I bring another point closer, then it's going to get close to being, the line between those is going to get close to being the tangent, whatever get close means. It's actually surprisingly difficult to explain to someone precisely, if you had to, what it means for a line to get close to another line? Like, don't really have a distance. They go through the same point. Why does all this stuff, says Jay in chat, get called calculus at A level and then have an identity crisis before switching to analysis at uni level? There's a philosophical difference there. This is probably not the right answer, but for me, calculus sounds like we're calculating stuff, and analysis sounds like we're analysing things and asking questions about them. Here and at A level, you do a lot of calculating. We give you a polynomial, you calculate its derivative. At university, we do a lot of analysing. We give you a function, you work out whether it has a derivative. So that person asking before about how do you know if a function has a derivative, that's more of an analysis question, analysing this function. Right, I said that's probably not the right idea, probably not the right answer, because I'm sure there's some actual etymology for calculus versus analysis, but let's pretend it's that. Let me make a point about A level. Good. So integration is the reverse of differentiation in the sense that if you differentiated something and if you differentiated P and you got Q, then to integrate Q, you're going to get back to P up to a constant. And there's this really annoying thing that later turns out to be important, but when you're at A level, the thing to remember for indefinite integration is that you need to add a constant. And that constant could be any real number. Okay, so for example, because we know how to go from x to the a down to a minus 1 x to the because we know how to go from x to the a down to a x to the a minus 1, that's how you differentiate x to the a. If we see a x to the a minus 1 in the wild and we need to integrate it, well, that's fine, we'll just go back up to x to the a plus a constant. I guess the problem is that we might not see x to the a in the wild and need to integrate it and get we might not see a times x to the a minus 1 in the wild and need to integrate it to get x to the a. We might see x to the a minus 1 without the a in the front, but that's not a problem. That just says that we need to remember to divide, because over here, if I had a 1 over a at the front, that's a multiple, so when I differentiate this, a comes down, a minus 1 upstairs, and the a out here, multiplicative factor, is going to cancel with that 1 over a. Or I suppose even more realistically, I might have x to the n, in which case the relationship here is add 1 to the power and divide by the new power. And that works provided n is not minus 1. Good, okay. Yep, definite integrals mean plug in the limit, stop limit minus the bottom, minus what you get when you plug in the bottom limit. And there's a geometric interpretation of integration as well. So derivatives is all about finding the tangent, integration is all about finding the area. Now, for MAT and at A level, people make a big deal about the fact that areas are positive, and that if your function is positive in some places and negative in some other places, then when you want to talk about the area, you're supposed to split it up and make sure you treat it really carefully and work out those areas separately. That kind of makes sense if you're talking about the areas of regions of space. But signed area, which is the same thing with plus or minus signs out the front, signed area can be negative. And I think signed area is the more interesting concept. You'll learn more about it later on. It's just pretty good. This is anti-differentiation. Git. I'm slightly terrified that I might be teaching people about integration. It's a bit scary. Someone asked before, I'm just genuinely not a teacher. Right, our interviews can be in person or online. Someone said in chat, interviews are online this year, and for the foreseeable future, I think, for Oxford. Okay. I've got some rules down here, and I think this is the end of my revision notes, which is good because we're revising quite fast. This one about switching the limits. So if I switch those around, that just brings a minus sign out. That's because up here, the first one is big F of B minus big F of A, and the second one is big F of A minus big F of B. This is a bit of a problem for people who are calculating areas. It means that you need to integrate left to right to find your area. This is not a problem if you're interested in signed area, because signed area can cope with that minus sign. In the signed area world, we would say the integral from 0 to 1 is positive, the integral from 1 to 0 is negative, and measuring the area depends which way around you go. I have some strong feelings about signed area, which I should not go and not say now. Okay, so got a bunch of stuff, a lot of different things, way more than we had last week or the week before, and actually you'll be pleased to know this is more content than we have for next week or the week after. So lots of stuff going on here. If people want to ask questions about this, then I think that's okay, but how about I also scroll down to some questions for you. If it's your first time seeing this, I've put together a list of questions. There are 13 on the sheet, 8 on the screen at the moment. The idea of these is that they're a little bit harder than things you do in A-level or equivalent. Some of them could be A-level questions, but some of them are a little bit harder than A-level questions. The idea is they're a little bit harder than A-level, but also a little bit more straightforward than MAT questions, so that you can find your comfort zone where you are in between. So you can say, this topic, I thought I understood it, but I need to revise it a bit more, or this topic, I'm ready to go and look at the MAT questions. I don't know. This used to be called a syllabus practice, but I found that I had to keep explaining the word syllabus whenever I called it a syllabus practice. Revision seems to be the word that people know. Someone in chat, while we're thinking about which questions to do, because I'm not sure we've got time to do all 13 questions on the stream. I want to do the ones that you want to see. Any tips for studying further maths? Says Akshith in chat. Started at jump from A-level maths to further maths seems massive. Depends on the topic, I think. My memory of further maths is that there's lots of different topics. It's got lots of different things. So it's possible that you'll prefer some of them to others, and you'll see them in some order. Probably not what order. Probably not the order that you find the most comfortable, to be honest. Which is sort of good news. It means that the big jump up is happening, and that it might stay around here, or even you might find things that you find more straightforward. I think the maths on further maths is a lot more interesting, which helps a lot. Quick look at chat. Chat is interested in 11, 7 and 12. 7 is, yes, okay, so 7's integration from first principles. 11 and 12 and 13 are new for this year as another request for 7 in chat, and then the last few. Okay, I kind of prefer the last few as well. They're kind of in difficulty order, plus also some new ones that I wrote are just stuck at the end, so I'm very excited to talk about ones I haven't talked about before. And question 7. Okay, how are we going to do this? I'm going to give people a little bit more time to express opinions or ask about integration. And thanks, Rowan. Good. Yeah, it's another request for 10 to 13, so it's kind of along those lines. 2 people simultaneously asked whether ChatGPT wrote any of these on screen. There. You put those chat messages straight away. No, I don't think ChatGPT wrote any of these. I did try. I just wanted you to differentiate a whole bunch of polynomials, and sometimes it asks you to find the turning points of a function that doesn't have any turning points because it doesn't know. It was quite irritating filtering through those questions because I had to do loads of horrible differentiation of polynomials that turned out to not have any turning points. So then I got cross and decided not to use any of the ChatGPT ones. I've been trying to learn to use AI. It hasn't taken my job yet. Right, we're going to talk about points A and B on the curve. And just while we've got chat up, great news, Jaquavius. You do not need to know integration by parts or the chain rule for the maths submissions test. Just in response to that question, before we do 7, whoof, way back up here, is the sum total of things that we're supposed to know about integration and differentiation for the MAT. There's not very many things. Good, right, now, whoof, 7. Okay, good, and I've accidentally, you can't see this, but I've accidentally minimized everything. Which doesn't sound like a problem, but is a big problem, right? Remove chat so that we can see the question. Split screen so that I can answer the question. We're gonna have a go at question 7. And then I think it was 10 to 13 or something after that. Okay, so the curve is y equals x cubed plus x squared plus x plus 1. Point A is fixed at 1, 4, which, quick check, is on the curve because 1 plus 1 plus 1 plus 1 is 4. Welcome to the Oxford MAT Livestream. And the curve, I guess, I want to draw it, I think. Looks a bit like that. 1, 4 is over here somewhere. Point B moves along the curve towards A. What happens to the line between A and B? Okay, so if I draw B somewhere else, like up here or something, and I draw the line between A and B, the thing we're looking for in this question is what happens if B gets really close to A? And maybe you can imagine in your mind what might happen as B gets really close. The graph, as I've drawn it, is kind of quite flat around there anyway. So you can imagine that maybe, after a while, it might start to look like something a bit more like this. If B is right in here, maybe the line will look like this, or something. Who knows? Well, we know we can work it out with maths. So the punchline is that the line gets close to the tangent at A. And the tangent at A has derivative, well, let's work this out in general first, which at A is 3 plus 2 plus 1 is 6. So the tangent is, I'm going to use my trick again. So I've written down a line where it's got gradient 6 and I've made sure it goes through 1, 4. I've done this trick before. It's good. It avoids thinking about values of lines. So what have I got then? That's my line, and I think the line AB, that's the tangent to A. The line AB gets really close to that. It ends up with a gradient that's very similar to 6, and a constant that's very close to -2. Now it's not very precise, that's not very rigorous, but it doesn't need to be. I was trying to get the idea here that the chord becomes the tangent. Quick question in chat. Somebody's asked: is derivative division and multiplication included in the MAT? I'm not entirely sure what that is, but I think if it's weird, then no. I don't know. So I think you're probably thinking of the chain rule for the multiplication one. I don't know what you're thinking about for the differentiation one. Possibly parametric differentiation. Never mind. Yeah, okay. I've had a thought, which is not how I would do this question, and I've had a thought, which is that maybe I could get you to work out the line AB. Oh, maybe don't do this. Don't do this. Like, we could just, there's nothing really mysterious going on here, right? Like, the line AB is something like difference in y's divided by the difference in x's, x, take away 1 plus 4. It's something like this. If my coordinates of b are b, comma, b cubed plus b squared plus b plus 1. So it's sort of this, and then the question is, okay, this is a bit of a mess. What happens to this function when b gets really close to 1? And the bottom's going to 0, the top's going to 0, so it's a bit confusing. It turns out to be okay, that you can work out that fraction. Maybe that's a fun thing to do, I don't know. If you work out that fraction for numbers that are really close to 1, then it will turn out to be close to 6. sounds like magic, to be honest. There's no 6s on there. Yeah. Okay, I think that's a homework thing then. If you want to try it, there's the line that actually goes through A and B. Try plugging in B equals 1.01. Does that work? I think it should work. Good, okay. What else did we vote for? That was question 7. That's differentiation from first principles. And then slightly a little bit from second principles. That's not what it's called. Okay. I think we're skipping 8, and are we skipping 9 as well? Yeah, so Ray in chat, let's put it on here as a sort of credit. Ray wants to use L'Hopital's rule, definitely not on the MAT syllabus. If you know L'Hopital's rule, then this falls apart as something. It stops being an interesting exercise if you know L'Hopital's rule. Credit where credit's due. You got your comment on screen, because I now have the technology to do that. Okay, are we skipping 9? I think we're skipping 9. It's a shame. No, it's not really a shame. They're just polynomials in disguise, right? One of them is a hidden quadratic. There was a request for 10, so I'm going to try and draw some pictures for 10. So the integral from -1 to 1 of f of x means that if I've got my function like this, between -1 and 1, it's the area underneath. Okay, and the integral from -1 to 1 f of minus x dx. That means that, well, f of minus x means a reflection in the y-axis. So now the question is, can I draw that backwards? That's not bad. Okay, reflection around like this, and the area this time, integrating from -1 to 1, is this area underneath the curve. But those are equal, because when you reflect, the area stays the same. I think that's probably the best way of doing this. If you know about integration by substitution, then this question falls apart and becomes not an interesting question. But if you know about transformations, and if you know about, which is on MAT, transformations of graphs is on MAT, and if you know about integration being the area under the curve, which is on MAT, then you can piece together this idea. This is an example of something that's sort of too easy to set on a MAT question, and also if I did, then about half of you would probably use integration by substitution, which would be very good. Good, okay. There was one request for 9, so I'm going to really quickly do bits of 9. Can you tell that I wanted to do 9? Thank you. Cheers to me. Let's go. So the one that I wanted to do, very quickly there, the third one on the screen is just a big power of x in disguise. Work with the powers. The last one looks clever, but actually just multiply out the cube and it's fine. Don't forget that cube root of x is the same thing as x to the 1/3. It's the first one that I wanted to talk about, because I've seen this sort of thing catch people out. Works like this. This is just not something I recognise, right? It's like a function divided by another function. But because of how these fractions work, I guess fractions are another sort of example, where you can write this like this, splitting out the x and the 3 separately to be separately divided by x cubed and then added together. And then these are not too bad, because this is x to the -2 and this is x to the -3, and I can now do these sort of polynomial or something. Not too bad at all. So it's sort of in disguise version of this, sort of simplified but made more complicated along the way. Okay. Thank you. 11, does that even fit on the screen? 11 is new for this year, and it's another transformations versus area sort of questions. I'm not sure I've got a very good precise notation for talking about transformations. Definitely not one that's going to make everyone happy. What do you think in chat? Yeah, it's sort of a polynomial. I think we're not supposed to call them polynomials if they have negative powers. I remembered that too late to stop myself from saying polynomial, but yeah, no, I agree. There's some chat going on, so I'm going to switch on chat quickly. Question marks on that. Yeah. You don't have to use methods in the syllabus. You have to follow instructions in the question. But otherwise, we don't mind if you use your own maths. Yeah, I think that's true. Yeah, there's a past question that I really like that, in some sense, if you know this big bit of maths technology, then it would be really straightforward. But the question tells you not to use it, or it tells you that you have to do it this other way. So that's a little bit different. Jay wants to know about why. Jay wants to know why. How can we know or think that integration is the area on a graph purely based on the basis of being anti-differentiation? Jay, you have noticed that something's a bit weird. Here are some facts you're told in school. Differentiation is all about tangents. Integration is the opposite of differentiation. Integration is all about areas. It's sort of weird that all three of those are true at the same time. They don't quite feel like they go together if you actually critically analyse it, if you stop and think. Areas, tangents, what? Piecing it together is one of the fun things at university. You no longer need to know the trapezium rule for the maths admissions test. Question in chat. You used to need to know the trapezium rule from that, which means that some of the past questions out there use the trapezium rule. It's one of the reasons that looking at old questions can get a bit weird, because occasionally they'll ask you to do something with the trapezium rule, which can be very scary. In the table of past questions on the official Oxford Maths Department MAT website, there's some notes, there's some comments that we added, kind of because people wrote to us and said it's very confusing that there's trapezium rule questions and it's all in radians, so we put these notes in to explain. This is the old questions as they were, but here's the kind of updated version. There's no mechanics or stats in MAT. Yes, no mechanics or stats. Yep. Right, okay, we've got some stretches in chat being suggested, which is what I was thinking about. So let's take this graph y is 1 over x. We're going to consider a rescaling of the graph, which means some sort of scaling or stretching. I'm going to do x goes to k times x, y goes to y over k or something. I'm trying to make it so that in this graph I'm thinking about it being xy equals 1 if I multiply up. So if I make the x's bigger and the y's smaller, I get another point that's also on the graph. Sorry, that was a bit mad. If you make x larger, then y gets smaller. That's a better way of saying it, right? So particularly this stretch, if you start with a point on the graph, with x and y multiplying to 1, then when you multiply these, you also get 1. So that's another point on the graph. So this kind of combination of stretches, pulling it wider by a factor of 10 or k in the x direction and squashing it in the y direction, gives you more points on the graph. If I take a whole bunch of points on the graph, drawing lots of circles, I don't think you can see. If you take a whole bunch of points on the graph and you apply this stretch, well, their x coordinates get multiplied by k, and their y coordinates get divided by k, but they all end up still on the graph. So after this stretch, we've got another bit of graph, which is a long way of saying that the integral from 1 to 10, 1 over x dx, that's this area over here. And the integral from 10 to 100, 1 over x dx, that's like this area over here. Yeah, I know that 10 is the same number as 10, so there shouldn't be a gap in between these regions, but I wanted to draw them separately. Sorry. That's this one over here. Those areas are the same because when you stretch by a factor of k this way and squash by a factor of k that way, you get the same area. It's pretty good. It's one of the nice things about the 1 over x curve. You can stretch it and squash it like that, stretching it by some amount, squashing it by that amount, and you get another point on the graph. So those areas are the same. It's just been stretched and squashed. Okay, that means those integrals are the same. And then the nice thing we can do, once we've seen that equals 10 to 100 1 over x dx, well, that's also equal to the integral from 100 up to 1000 1 over x dx. Because of the same scaling, I can make k be 10, I guess, again, and take this bit of area and stretch it and squash it again, and get another bit that's also the same area, and keep going. Which means that if I add these things together, I can make that integral from 1 to big N of 1 over x. I can make that really big, because if I make n large enough, some huge power of 10, then it's going to include all of these sections, each of which, although they're very short and very wide, each of these has the same area. I thought it would be a cool thing to show you, or put in here. For MAT, we can't actually integrate 1 over x. It's the one you don't know how to integrate. If you do know how to integrate it, then this question just falls apart. It's not interesting. It's not a fun thing to do. But look how it's worded, so that it says by considering a rescaling. So it's sort of telling you how to do it. And the word deduce there also means using the previous part, or hence is another word that we use to say do the previous part. So I've tried to word this question in the way of, I know there's this other way to do it if you know how to integrate 1 over x, and I'm trying to make sure that you do it the way I'm thinking of, so that we practice this stretching and areas idea together. Will we need to know about integrals as approximations to sums? No, but it is cool. This is a person in chat suggesting some cool maths that's not on the MAT syllabus. Okay, and then quick look at these two. This has been added because I was talking to a student and they were surprised. So I added this to this, so that before you even become students, you can be surprised by it now. The surprise is that we can do integrals like this, or at least we can make them easier. The rule is, if you see a fraction where the power of x on the top, some polynomials on top and bottom, if the power of x on top is the same or bigger than the power below, you should do some polynomial division first. That'll make your life much easier. X squared is sort of like 1 plus x squared minus 1. So this is but that first thing's just 1. So because that first thing's just 1, this is the integral, which is just, I think, 2 minus, and then this thing here is I3 or something. So it's like totally falls apart as being something quite nice. Suggestions in chat are adding 1 and a minus 1. Yep. Cool's doing partial fractions, which is also not on MAT. Theo wants book recommendations. Sorry, chat's popping off. Right, let's have a look at chat. Not really for this level of maths, I think, Theo. Yeah, so people in the chat know about the integral of 1 over x. I didn't read it out, but some of them know the integral of 1 over x. If you know that it's log x, then you're fine. Hi Kai, good luck with your A-levels. Good, okay. Partial fractions turns out to not be an entirely great way to do this integral. Actually doing the integral I3, not on MAT, so let's not worry about it. It's nice. Okay, last one, which I didn't give a name to, but the integral x to the 4 over 1 plus x squared, 1 to 3, slightly under, there we go. So you can do some polynomial messing around with this first, even without the integrals. In fact, let's get rid of the integrals. I think it's just a fact about that function. That's the same thing as, I'm going to write down an x squared over here, because x to the 4 over x squared kind of looks like x squared to me, but it's not directly x squared. If I imagine multiplying this back up, I would get x to the 4, and I'd also get an x squared. Bother. So I'm going to subtract an x squared over here. And then when I multiply up, if I imagine multiplying up, I would get exactly the thing on the left-hand side. I'd get my x to the 4, I'd get x squared minus the x squared, that's what's on the left. This is pretty neat because that x squared, that's something I can integrate, that's just a polynomial. And this thing over here, with the minus sign, that looks a bit like I4. So I think this new integral turns out to be the integral of x squared from 1 to 3 minus I4. Okay, that's like 8 2/3 or something. Okay, this is actually quite a good trick of combining integrals together. I've realised that a better way to say question 12, a better thing to say would be just take those two integrals and add them together. If you add them together, then the 1 and the x squareds upstairs add together, because fractions are nice. Fractions with the same denominator are nice. So if you add those things together, you get 1 plus x squared over 1 plus x squared, which is just the integral of 1, which is the number 2. Maybe adding them together first might have been a better way, but hey, this kind of polynomial division is a little bit nicer. Ray knows about the integral of 1 over 1 plus x squared. Everyone's saying good luck to Kai. Any equivalent? I don't know what MF19 is. Sorry. Yeah, cool. Okay. There's a question about a maths unit or something, but I don't know what it stands for. Sorry. Okay. Whew. You can do quite hard integrals, or at least relate together quite hard integrals like this. If you use a combination of this trick with this method, compared also with the one from before with x plus 3 over x cubed to recognise some easier terms, you can get quite far with some things. Just for a kind of extra homework or something, you might like to see what happens if you put in something like x to the 6 over 1 plus x squared. Can you relate that to previous things as well? This is now sort of an extension question for a revision question, which is not how the worksheet usually works. Usually we go revision, then math, then extension. Right, okay. How are we doing? We're a quick breather because we hit about an hour and we've done some revision questions. There's some that I didn't do. Sorry about that. Let's have a quick look at ones we didn't do. Catch your breath, and then in a moment we're going to look at some math questions. I've picked out what I think are quite reasonable math questions for this one, so I'm looking forward to smashing through some math questions. Have I still got chat? Is that working? Yep, good. Okay, I can see chat. I'm going to drink some water because it's quite a lot of talking. Yeah, so in chat there's a question suggestion. Question suggestion, let's put a chat on. Don't forget to drink water. Right, what do I do? If you've been looking at a screen for the last hour, take a quick break to look at something that isn't a screen. Remember, you're human. Someone in chat has set us the question of doing x to the 2n for all n. Keep going. They kind of relate together quite nicely. It's not too bad at all. Your instruction to keep going is noted. Put a general polynomial on the top, find a general formula. Don't do that, that sounds horrible. We skipped quite a lot of standard differentiation questions about tangents and normals. People were happy with the normals. Did anybody do the M1, M2 trigonometry thing? There must be someone, right? After we did while we were doing some revision questions, did you do this trigonometry thing? How do I divide x squared by 1 plus x squared with long division? Go on then. Which one am I dividing? This is not going to look good, is it? It's going to look bad. Big number goes in here. Small number goes in there. I guess 1. And then you subtract it. I don't know what I'm doing. That's not very convincing. I'm even going to delete it. There we go. polynomial division, and other fun things. I think what I'm actually imagining is what would happen if I multiplied it back up again. That's probably not the best way to think about these things, of doing this manipulation on these rational functions, polynomial divided by another polynomial. Probably I'm supposed to think about it in terms of polynomial division. Something I've had to realise recently is that I'm not as good at polynomial division as some of my students are. Some of my students are just really good at polynomial division. It's a bit surprising. Polynomial division. Oh, it was a remainder. Oh, thank you, chat. Maybe I shouldn't have deleted that. Treat the remainder as a bit over the divider. It was a remainder, of course. Thanks, chat. Right, okay. Yeah, the question about time zones. Matt's only done once a year. There's only one Matt paper each year, and it's in roughly October. We should do it everywhere. Sorry, Basil. You should never feel silly about asking about polynomial division. Polynomial division is hard. I've just said I can't do it as well as my students. That particular one had quite small numbers, but that doesn't make it an obvious concept. Right, good. I'm glad that people can ask questions. I think in chat it's easier to ask questions. It's got kind of set up, right? It says Q&A at the top and it says ask a question here. Anyway, right, okay. That was the break. I'm going to switch chat off again so that we can see this lovely Matt question. Here's all of it. Should we read it together first? If you've already downloaded the worksheet because the website's working for you, then you could have a go at this Matt question. Let me know how it went. If you haven't seen it, we're going to read it together in a second. Okay. So this is question 3, which starting from 2023, all applicants are going to do question 3. Question 3 has sometimes in the past been about calculus, integration and differentiation. Sometimes slightly different, slightly a bit more geometric, but something like this. Okay, so it says, let the integral I, open bracket, c, close bracket. Wait a minute, this is a function. It's a function of c. Let's read on to see where the c is. The integral from 0 to 1 of x minus c squared plus c squared with respect to x. So it's already a bit funky because it's integration with respect to x, but there's a constant in there, c, except on the left I'm thinking about changing the constant. So it's sort of constant for any in particular c, I'm going to treat it as a constant when I do the integration, but maybe I'm going to imagine changing c. It's one of those things that's maybe not worth worrying too much about. If you don't like big I open bracket c close bracket as notation, you are welcome to rename big I to small f, and then it looks more like a function, right? F of c. Okay. First question is to sketch this, which I think corresponds to c equals 1. It's the integral. And sketch this quadratic. Fine, brilliant. Okay, we can do that, right? Show the area represented by I of 1. Okay, something's to the c of 1. They're checking that we understand what this area does. 2, why is this thing positive? 3, actually calculate it. So I quite like the way that 2 says without explicitly calculating it, and then immediately the question asks you to calculate it. 4 wants the minimum, so at that point I'm probably thinking about calculus already because I've done some integration. I might think about differentiation. A little bit awkward that it's I of c at that point. And then the last part looks tricky. It says the maximum value of I of sine theta. As theta varies. We'll get there as we get there. Sometimes it's nice to read through the question. I know that when I was at school, my teachers would encourage me to read through the whole question, or even read through the whole question book, all of the questions before you start, so you can think about what you're going to do and put them all in the back of your mind. I've never been very good at that myself, because when I read the question, I really want to start doing the question. I guess I'm worried that I'll forget that I've had an idea, and if I don't write it down, then I might not have the idea again. I guess I have weak memory or something, and I don't trust myself to remember this stuff. So I just said what I think at the time were pretty insightful things, but I didn't write any of them down. So that's what we're going to do now. If that's okay with chat. Ray in chat's telling me about rotation matrices. Oh yes, because I asked about that gradient thing again. If you know about rotation matrices, then you know this is another example of using some high-powered mathematics. Somehow feels a bit like, well, I can't really appeal to like the hierarchy of maths concepts, right? Because we haven't done that. Okay. We're going to do this very first part because I'm going to sketch a graph. If you've sketched a graph at home, please could you let me know in chat, what did you check when you sketched your graph? What were you thinking about? You can say nothing if you like. You can say, I just drew it. That's fine. But you could try listing things that you want to look for. Quadratic, So quadratic with positive coefficient of x squared. If I multiply out that square, positive coefficient of x squared, so a happy quadratic. Looks like the minimum is at 1, 1. Okay, I'm going to draw it. Good. One of my better drawings, I think. And I think that's about as much as I would think about it before drawing a drawing. Maybe I'm not being very careful. For example, I haven't thought about the limits, or the y-intercept, or the x-intercept, or other things. Here we go. Yeah, turning point, look for roots. Yeah, look for roots. What happens if you look for roots? It's not got any roots, because you can't do the square root of -1. Yeah, people did turning points, yeah. Somebody's talked about transformations. That is brilliant, I love that. So this is a transformation where you take, yeah, that's really good. So you start with x squared, turn it into x minus 1 squared, and then turn it into x minus 1 squared plus 1. That's really nice. That shows you it's happy quadratic, and you know how happy it is. Translated 1 to the right, and then 1 up. Good. Okay. Yeah. Translations, brilliant. Okay. There's a couple of people thinking about translations. That's really nice. I thought about minimums. If you thought about turning points, did you think about it using complete the square, because it's already been complete the squared? Completed the square? It's already in that form, or did you think about differentiating it? I guess those are the two ways. I think for me, because it's been written like that, I was thinking about 1, 1, because I could see the ones. But it's quite tempting to also even multiply it out, right? If we multiply it out, we get x squared minus 2x plus 2, which actually looks harder to sketch. It's the same graph, but harder to sketch because I'm not going to notice the transformations. So a couple of people in chat who told me about transformations writing up. That's harder to spot if you multiply it out. But maybe it's easier to work out the turning points, right? Another vote for translations. That's brilliant. I'm really glad people were working with translations. And Josh used completing the square. Okay, there's quite a few votes for complete the square. In the middle there, a question about the open day. There's information about the open day on the maths website and on the Open Days website. If you search for Oxford Open Days and find the departmental programmes, we're doing talks in the morning. The y-intercept is at 0,2, yes. Which on my picture is not to scale. If I even got it higher up, oh well. Not my greatest work. Yes, okay, good. It's got no real roots. Good, right, I think we've got this. We were supposed to draw it over a particular range, so I might mark in that range. I suppose mine is not to scale at all, so I could do this quite a dodgy way. But I think, yeah, so hard question that's not really in the question. Should it be higher up over here or higher up over here? I've drawn it going to the same height on both sides. Was that a good idea? I can plug these numbers in, I suppose, to work it out. If I plug in -1, it's like -2 squared plus 1. It's 5. If I plug 3 in, doesn't it way bigger? Neither, because if I plug 3 in, it's diagram's just getting worse and worse. It's possible that I should try harder. Yeah, okay. Good idea. It's the same value on both sides. That is, believe it or not, a sort of rectangle I've drawn in dotty lines over the top of that picture. Those 2 points are supposed to be the same height, and the other two are supposed to be not at the same height. Gosh, right, okay, we should stop looking at my quadratic quite soon. Yeah, right, okay, so someone in chat, an anonymous person, says that 1 is the midpoint of -1 and 3. Maybe they are aware of some brilliant symmetry of quadratics, which is that quadratics have reflectional symmetry in the line through their turning point. The left side of a quadratic looks like the right side of a quadratic. Someone in chat says, I got all of this math question correct. Hey! Let's put that on the screen very quickly. Hey! If that's your first time getting a math question correct, hooray! Yeah, distance from turning point is important. I've seen that used in a question at some point. It's kind of nice symmetry of the thing. It comes from the idea that x squared is symmetric, right? Squaring a negative number is the same thing as squaring a positive number. More or less. That was a terrible thing to say. Squaring -3 is the same thing as squaring 3. So that kind of symmetry comes through. Yeah, x squared is an even function. People in chat are saying even function. I think this one's not an even function. Is an even function based on the turning point. I'm not really sure I've heard that phrase before, but sure. Okay, x squared is an even function. That's what's going on here. We were supposed to draw in this area representing the integral from 0 to 1, which on my graph is awful, because that's the bit of my graph that I drew the worst, but on your graph probably looks like some curve coming down from 2 to 1. Good. Over to chat, I think, to explain why this thing is always positive. There is a wrong answer, I suppose. Yeah, I can think of a wrong answer. I'll let people put things in chat. But yeah, okay, well, why is this thing always positive? Yeah. Okay, it's nice when there could be a plausible wrong answer for a question. I have no idea if anybody's going to say the wrong thing, but we'll see. This is not a trap, I'm just interested. Okay, so we've got I of c at the top of the screen there. It's x minus c squared plus c squared. And I'm getting chat to explain it, so I'll switch on chat as well. People are telling me now in chat. Okay, so the minimum is the minimum always at x equals 1? I suppose that I of 1 is positive because the minimum's at 1. I think the minimum changes when you change c, the minimum goes to c comma c squared, but that's positive, so you're making a great point. Why? You could do the b squared minus 4ac, you could check the determinant of that quadratic, but look, it's in completed the square form, right at the top there. It's in completed the square form, and it is two things that are positive added together. Another example of complete the square form being great. I'm really bad at saying that phrase today. Excuse me. Yeah, sum of two squares. Minus b over 2a. Oh, that's the coordinate of the turning point. Somebody's imagining multiplying out. In general, if you multiply that out, you get x squared minus 2cx plus 2c squared, and the turning point is at c. But it's more obvious to see that the turning point's at c for the function inside the integral at the top. The turning point's at c kind of because of complete the square stuff. Completing the square, very good. It's got no roots, it's positive quadratic. Yep, good. Okay. I don't know how MAT compares to Singaporean H1 because I'm not very familiar with that test. Sorry. But if it's like AS level maths, then it's probably quite similar. Except Matt's got, a lot of weird problem solving stuff going on, which I don't know if H1 does or not. Good, okay. Nobody has said the thing that I was worried that people might say. Here's the wrong thing that I was imagining. I was worried that people would say I of C is an integral. Integrals represent areas. Areas are always positive. See, so that sounds like a true maths argument, but it's completely nonsense. It doesn't work at all. I of C is an integral, correct? Integrals represent area, not quite correct. Areas are always positive, kind of, I guess, depending on what you meant by area just now. So I is positive. It's hard because it ends with a correct statement, starts with a correct statement, and a couple of lines in the middle are a bit weird. And that's really hard to spot if you're writing your own arguments. It doesn't work because integrals can be negative. Areas might be positive, but the integrals can sometimes be negative. This one isn't, but they could be, in which case it's representing some sort of signed area. Okay, yeah, good. I'm pleased, by the way, lots of people in chat there. I don't think I read out everything in chat. Loads of people put great things. Okay, good. Thanks for joining in. It's really not the same if people don't join in. It's even more of me. Okay, we've got 3 parts of this question to go. I need to calculate I of C. My setup is not fantastic for this. Let me just copy down I of C over here. I'm not going to write down those outside brackets. Okay, we're going to calculate. I think at this stage it is easiest to just multiply it out. Possibly there's someone in chat who has some clever technology for integrating things like this. I think I would just go for it as the integral of x squared minus 2cx. Oh, I had to say this out loud a moment ago. Here we go. From 0 to 1. I would encourage you to do this very carefully and to do each term with the proper sort of respect that it deserves, rather than just hitting it with factors of 2 and stuff because you vaguely know what happens. But you end up with some sort of quadratic. So signed area, for Basil in chat, who's going to have to look at signed area. Signed area has the advantage that it's the same thing as integration. So you already know about it. You just have to accept it in your heart. I might do that if we got time at the end. I'll do the side note. Okay. So there's a quadratic here for what I of C is. So this is the thing we've been arguing about all along. All the steps beforehand. Explain why I of C is always positive. You see, but in part 2 they say without explicitly calculating it, which is good. It's very tempting. Otherwise, I might be tempted to go and complete the square on this. So write down something like this. 2 over 16 is 1 over 8. I've also got a third. My goodness, so I need to add on the third and take off the factor of 1/16. It's possible that there's some sort of method that I should be using for this, right? Not 16th, 8th because of the 2. It's possible there's some sort of method for complete the square that people might know about, b squared minus 4ac divided by a or something. I guess I'm always just doing them by thinking on my feet and trying to make sure that the thing is equal on both sides. Right, good, okay. So if we'd been allowed to calculate I of C for part 2, I would have done something like this. I would complete the square and say, aha, I of C is just a quadratic and it's positive. Okay. And then it asks us for the minimum. And once you completed the square, finding that minimum, right, okay, well, 5 over 24, isn't it? Because this square could be 0 if C is equal to a quarter. There's a turning point at 1/4, 5/24. Let's do it with calculus as well, just for fun. So calculus would say we're going to come in and differentiate this and find the turning point. Where the value is, and then I'm going to go and plug in 1/4, which I'm not particularly looking forward to doing. That's even worse than the previous sum I just did, where, goodness me, did that work out to be the right thing? Yes, it does. Okay, tiny bit of calculus, since this is the integration and differentiation live stream. Nicola in chat's asking about tips for getting through first year calculus and linear algebra during the summer. They say math major, and I'm not sure if they're already doing a math major or if they're about to start doing a math major. sort of matters which one. I've got revision tips, but if you're learning it for the first time, then it's totally different advice. Okay, we've got down to the minimum of a quadratic. We've got one part of the question left, which is looking for the maximum value. If we're paying attention, we see that it says maximum now, of I of sine theta. Okay. So a tricky thing to do would be plug in sine theta. We've got I of c, right? Plugging in sine theta gives us some expression in terms of theta, and then try and think about the maximum or minimum. So that's one way we could do this. There are other ways. I think I'm going to get chat suggestion about what to do. So we could do this thing where we plug in sine theta and then do some trigonometry stuff. Or we could do this a little bit differently. Nicola Wright says they're learning for the first time. So if you're about to start your math major, then at some point you're going to learn lots of linear algebra and calculus. The calculus exercise I would give you is try and work out which differential equations you can solve. You can solve quite a few differential equations by the time you're about to head off to university. Try to work out which ones they are. Because later on at university people are going to show you some more differential equations and teach you to solve these quite big categories of differential equations. So having some sort of awareness of which ones you can already solve is pretty good. Chat is doing great over here. It's also just quite a fun exercise to remind yourself of your sort of differential equation powers by that stage. As you're heading off to university, which differential equations are going to scare me and which ones are not. Yeah. Okay, so only between 1 and -1. So the suggestion is to, I like Josh's suggestion of drawing a graph. So sine between -1 and 1. Sine varies from -1 to 1, so from the furthest point from the turning point, calculate. Okay. So it feels like people might have this kind of mental image of what's going on in this quadratic. So this quadratic looks like it's got a turning point at 1/4, 5/24. Good. Okay. I think I've drawn that right. So its value over here at -1, if I go all the way out to -1, its value is going to be a bit bigger than its value over here at 1. And the turning point is kind of not relevant because that's not a maximum. The turning point is a happy quadratic in terms of C. A turning point is not relevant. So we've got this other thing going on. Sine varies between 1 and -1. And it's actually quite nice that you don't have to worry about the value of theta because we just want the maximum value out the end. Let's plug in the endpoints and see what happens. I need to remind you what this function is, I think. It's this. If I plug in 1, we get 2, take away 1 is 1, which is the Oxford MAT Livestream, plus a third, we get 4/3. And that is -1, we get, that's 2 again, this time add 1, as it's definitely going to be bigger, and that's 3 1/3, which is 10/3. It's bigger over there. There's this general rule about quadratics that the further away you get from the turning point, the larger the value is. It's a fact about quadratics. You've got to be a little bit careful in general with weird functions that aren't symmetric. Symmetries of quadratics, there's probably a math question in there somewhere to just do sort of playing around with all the nice things you could do with quadratics. And then maybe the last part is, here's a function that's not a quadratic. It doesn't do the nice things that we've been talking about. Basil in chat wants to talk about, just from that complete the square form, we want to make this bit, which is the only place C appears in this expression, we want to make this bit with the square really big. And we make that really big by making C really far away from 1/4. That's the symmetry of x squared that I'm talking about, the one that you make this square, you've got that x squared maybe, if you make that really large by making x really far away from 0, making C really far away from 1/4. Where did my 4C -1 come from? Yeah, it was a bit terrible, wasn't it? I wrote out this quadratic, and then I suppose what I'm calculating here is the derivative of I of C with respect to C. And I've done it term by term. So this 2 comes down 4, and then minus C just goes to -1. Okay, so -1C to the 0. I did that way too fast, and given this is the integration and differentiation live stream, I should maybe have put more time into that one bit. Good, okay. Yeah, to complete the square is good. Plugging in 1 and -1 is pretty good. Josh wants to know what my favourite degree polynomial. Wait, what? What's your favourite degree of polynomial? I think it's 3 at the moment, although 5's pretty good. 5 is pretty... It's going to have to be 5, isn't it? 5th degree. Amelia, did I help? I did it way too fast the first time. 4c minus 1. Have another go. Oh, right, yeah, hang on a minute. This is an important comment from an anonymous person, which sort of makes sense, I guess. But just to check, I won't remember, I won't remember or care, both. I mean, I can't promise I won't remember, but my memory is pretty bad. Or care about names from live stream streaming mission promoters. Obviously, no. I have no idea whether you're using your real name. So it would be really stupid of me to try and keep track of people's names and what's going on and then look at applicants. That would be stupid and also kind of evil, right? Because this is about learning maths and practicing. If you say something really silly from the silly us, and then we're going through it, remember, you once said something about adding, no bias. Yeah. No, you're fine. You can carry on being anonymous if you like. But for example, I'm not going to single out Josh at interview or something because it's probably a bunch of Joshes. Right, okay. Yeah, interview question: what's your favourite polynomial? Ask it to every Josh. Terrible idea, really bad. This goes for a lot of stuff that we do. Kind of most of the year I'm just trying to tell people math stuff. I have one more thing. Oh yeah, okay. We've also said really stupid things. I've said a lot of stupid things, including quite a lot that are on stream, so it'd be really, really mean of me to try and make anything out of other people saying silly things. Yeah, cool. What was that? Was that 30? For a long time I thought 39 was prime. I have a whole story about thinking 39 was prime. That's probably my lowest point. It's probably during a university interview, and I tried to simplify 5 to the power of 4 divided by 6 to the power of 4. It was a dice rolling probability thing, and I tried to simplify it by crossing out the 4s. Do the same thing top and bottom. That's how fractions work. So 5 over 6. I did that during an interview, and then they still gave me a place afterwards. So you'd be surprised the kind of silly things that silly mistakes that you make, and yet also doesn't really matter. There are about 100 people, so Brian, there are about 100 people doing interviews just for maths at Oxford. Definitely not just me. That would be awful. Hey, right, good. Homework, and I think I put it as an extension question, which is not here. Oh, there's the hint. Here it comes. There we go. What we had here was a quadratic 2c squared minus c plus a third, and we plugged in sine theta, and there's different things that can happen. I'm not going to answer this question on the stream, but thinking about the different cases of what might happen, depending on A and B and C, it's quite fun in a way. You can make weird things happen if you change the numbers A and B and C. Probably a fun way to explore this would be to stick it into Desmos or something, have some sliders for A and B and C, with sine thetas in there, so that it's like some sine shape and changing A and B and C. I sort of want to do that now, but I also want to do my signed area thing. Let's try and do everything, right? Let's just try and do everything. So it'd be something like, this. Why is A sine x squared plus B sine x plus C? Yeah, this is my idea of a fun time. There we go. So if you change A and B and C, different stuff happens. And explaining these different ones. Some of these, your intuition is correct about where the minimum should be, and some of them, well, it's complicated. How many turning points are we looking at? Quite a few, right? And changing these, does Desmos let me? Oh yes, Desmos lets me switch all of them all at once, so that's fun. Good, right, okay, that was just as fun as I thought it would be. Okay, back to the maths. We're 2 minutes spare, that's allowed. Back to the maths. We've got another math question coming up, I think. It is 6:30. and we've got MAT 2009 question 3 ready to go. Yeah, it looks like other polynomials. Okay. We've got some sketching to do. We've got some functions. These ones are defined f subscript n. The n is sort of keeping track of like a sequence, I suppose, of functions. There's a f1, there's an f2, f3, things like that for different values of n. It's a way of getting around the idea that x is still the input number, but n also matters. N is on the right-hand side of that expression. So it's sort of like there are two relevant bits of information. What's the value of x, and can you remind me what value of n are we talking about right now? So those are both shown on the left there. But because n is a positive whole number, we're thinking about that as like a sequence of functions. Although I say that, you don't actually have to think about that at all, as long as you're happy to plug in values of 2 or n or x. Values of 2. As long as you're happy to plug in values, we're gonna be fine here. For example, f2x is just going to be 2 times 2 is 4 minus 1 is 3 quick maths, minus 1 squared. So it's just this. And now there's no weird n stuff going on the right-hand side. Our first task is going to be to sketch that function. Next up, we're going to sketch it where n is some large positive integer, and we might have to think about what that means as n gets really large. But again, nice sort of sketching exercise. Probably going to break it down in stages. Earlier people were talking about transformations, and it's inspired me a little bit to think about transformations of this graph. Or maybe I'll just plug in some values for x. Part 3 of this question wants us to integrate that in general for n, and then it gets quite algebraic. 4 has got some algebra to say. We're told that it satisfies this inequality. Briefly looked at inequalities a couple of weeks ago. Show that our expression and explain why. And then when a is equal to 3 over 4, find the smallest possible value of b. Oh gosh, okay, so we're going to have to do some inequalities at that point. Hopefully by that stage I can see we've calculated the integral. So at that point probably all the calculus has gone away and we're just doing some algebra instead. Hopefully I won't have to think about any integration by the time I'm down here. Okay, sometimes it's nice to work out what sort of skills you're going to use. Amelia's got a good question in chat. Let's go for that. While you're having a go at sketching this at home, I'm going to answer a question. Can I put the question on at the same time? Just about. Amelia's question is, how do you approach the questions that have 2 to the 2023 or something similar? They seem quite popular with math or math challenges. We don't do them that much on the MAT. Is that true? Yeah, no, we don't do them that much on the MAT. Math challenges in the UK, the UKMT really likes a question like that. It usually means any large number. Sometimes it matters what the number is, but a lot of these facts from math challenges are just true for any large number. So then the trick is to think about large numbers in general. For example, if I ask you the question, prove that there exists a 2000th prime number. That sounds really hard. It sounds like you're going to have to work out 2000 prime numbers. Prove that there exists a 2000th prime number. It's pretty tough. But if you just prove that there's infinitely many prime numbers, then there's going to be a 2000th one, and that's easier and different. None of that's math. Yep. Okay. Factorizing part 4. Okay. Request to do part 4 in detail. Okay. None of that number theory stuff. Let's be careful. What do we expect you to know for MAT? So we expect you to be able to add together small numbers and maybe to talk about whether things are divisible by other numbers or not, but nothing too weird. It's a good question, number theory. How much number theory do I think people know? Not very much number theory. Okay, right. Let's have a go at this. Curve sketching. I think I'd approach this in 2 steps. X cubed minus 1 and then square it. We can definitely do x cubed minus 1. Let's briefly think about what squaring does in general. If you take some function, lots of different values of x, and we square it all, then I guess the output, everything is now going to be positive. Big things square to big things, 0 squares to 0, 1 squares to 1, other things square to their own things. So I think first I'm going to try and draw x cubed minus 1. I've drawn terrible axes for that, haven't I? Because x cubed minus 1 goes through minus 1 on the y-intercept. And looks like this. And it's got an x-intercept. Where's that? That's a 1 over there. Okay, that's relevant because when I square 0, I'm going to get 0. When I square minus 1, did I say 1? I meant minus 1. And when I square minus 1, I'm going to get 1. So now I've got some ideas about how to draw x cubed minus 1 squared. I think it's going to go through 1, and it's going to go through 0. And it's going to be really big over here, where the function over here is large. This looks to be really large. I'm going to draw it going woof like that. So put that on the soundboard. Okay, over here it's negative, but negative things get squared to positive things, and these ones are more negative, so there's going to be more positive. Maybe like this. So then I've got this question about what's the bit in between? What's going on over here? Where the function is between, the thing inside the bracket is between minus 1 and 0. It's increasing from minus 1 to 0. So this is going to decrease from minus 1 down to 0. And I'm going to draw it nice and smooth, I think. I'm going to draw it with kind of smooth, quadratic-y kind of point there, because I think this is actually just some polynomial, and polynomials have got smooth turning points. Point of inflection, that's a good word, and that's what's going on in here. That's an example of a point of inflection. You could differentiate and find some stationary points. That sounds fun. Let's do that. So if I multiply it out, there's nothing too mysterious going on here, really. It's just this. So if I multiply it out and then do, I don't always love this notation, but I'm going to try and differentiate it. Okay. Then I can see that this is 0 at 1, or if, oh gosh, x to the 4 minus 1 is 0, so it's 1 again? Yeah, 1 again. Or minus 1? So it got no derivative at minus 1? Mine definitely does. Oh, okay. So it's something weird going on at minus 1. Now I'm worried about my sketch. Has it got some sort of weird inflection point going on at the left? Maybe it does. So it'd come down to, I'm wishing I hadn't differentiated it now. Help me, chat. It's 6x squared. Is it 6x squared? Oh, that would fix everything. Yeah! I can't differentiate. I forgot to subtract 1 from 3. Brilliant. Oh, great. Oh, so that's repeated it. Oh, that's solved everything. That's got the 1 and the x squared. Oh, that's great. I'm glad that it turned out to be a stupid mistake. I'd always take a stupid mistake over a... Yeah, thank you to people in the chat who pointed out that I can't subtract, but very nicely. That's good. Okay, right. You have to promise that you won't remember my name. Right, okay. So it's got a stationary point, or a stationary point at 0 as well, which isn't very obvious on my picture, because I wasn't aware of it when I drew my picture. Okay. Good. There's a suggestion in chat. An anonymous person has got an opinion, which I want to read out. Differentiating this is like cutting an apple with a chainsaw. The previous thing about transforming graphs is a bit more elegant. It's an opinion you can have. If you're going to work as a professional, like chainsaw operator, who does that? Anyway, never mind. Yeah, okay. Practicing using chainsaws could be good if you want a job using chainsaws, to use the metaphor, but it's not gone very well for me using that metaphor, so we're moving on. Okay. We're also asked about fnx, where n is a large positive integer. Why have they told me positive? We already knew it was positive, right? Okay, it says whole number at the top, and now it says integer. That might just be a typo on my part. Does the original question do that? It's really interesting to me now. I'm going to get distracted by this. But thinking about large values of n, you could, if you like, choose a value of n, like choose 100 or something, and just see what happens. Although when you do that, you probably think about it in the same ways that you would think about it if you were just imagining a general large number for n. So if you pick a big number, make sure it's one that doesn't take you very long to write down, because writing it down is, I think, not actually that helpful. Yep, no, it does say whole number the first time, integer the second time. That's not a typo that I introduced. Good, right, okay, same thing. So what do I need to change when n is a large positive integer? I'm going to try and draw over the top of both of my pictures. I'm using pink this time. So x the n minus 1. So I know that pink can be a little bit hard to see, but I'll try and describe what I'm doing at the same time. So where's it the same? It's 2n minus 1, isn't it? Luckily, pink is hard to see, so nobody spotted that. When x is 0, this is still minus 1. When x is 1, this is still 0. So we're going to do both of these. And it's also going to shoot up. I think this power is huge, so I reckon it's going to shoot up faster. Maybe I should work out how much faster. No, I'm just going to draw it going to infinity really quickly, really steeply. And over here, it's going to go to, well, I suppose a translation down of some very, very odd curve. So I'm going to draw something like this. Large powers like this take numbers between -1 and 1 and send them basically to 0. So if you have a number between -1 and 1 and you raise it to a huge power, that's like doing a lot of dividing, right? If you have 1/5 and you raise that to the power of 100, then it's like dividing by 5 100 times. So everything in between -1 and 1 ends up near 0, and then translated down by 1, of course, for this one. Yeah, so because 2n minus 1 is an odd number, good spot. Because 2n minus 1 is an odd number, it's got this odd symmetry, but then shifted down by 1. Okay, and sharper. Okay, we've got the challenge to square that now, which between -1 and 1, the thing's pretty flat and close to 1. So I'm going to draw something that's pretty flat and close to 1. Over here, it's going to shoot up very suddenly to enormous numbers because these are very negative when we're squaring them. Over here, something's going to happen because it's 0 down here, where I'm squaring 0, and it's extremely positive over here. But I think it's got to come down from basically 1 down to 0. So coming down from basically 1 down to 0, as this pink line suddenly changes from -1 to 0, the square of -1 is 1, the square of things in between gets smaller, and then it hits the square of 0. So this thing being sharper is this, I suppose, intuition that the difference between 0.99 to the n and 1.01 to the n, if n's a small number, then there's not much difference between those things. They're both actually pretty close to 1. But if n's a large number, there's a big difference between 0.99 to the n and 1.01 to the n. If you haven't played around with this before, I know I just did this, but I'm going to have another go at it, which is just grab, and I don't need all the screen for this one, just grab a bit of Desmos. Oh, I'm going to get T1 on the screen. Okay, let's go. So if I just throw an x to the n on here, oops. Okay. If I just throw an x to the n on screen, then you get these kind of quadratics and cubics. And the thing that the kind of intuition you develop later on is that ones with large values in here are very, very steep, and also very, very flat between basically -1 and 1. And the left bit there is flipping up and down for odd and even numbers based on the fact that negative numbers to even powers are positive. But there's this idea that around here it's getting really, really steep and really, really sharp. So if I put in something like 200 or 2000, then it's getting really quite boxy. That things between -1 and 1 are basically getting set to 0, and things outside are shooting up. If I zoom in, it is still slightly curved around there, but my intuition is that this thing's basically like box shaped. So large powers of n have got this slightly weird behaviour where the even ones are basically bucket shaped, and the odd ones, I don't know why that's happened. The odd ones are basically Z shaped. Oh, I do know why that's happened. Was it doing that before as well? Oh, I've worked out why it's doing that. Yeah. Yeah. It's because I've set up hotkeys and then forgotten about my hotkeys. Every time. Someone in chat wants to do a Fourier series, which is some university maths that will help you a little bit, but not a lot. Yeah, so there's the sharpness. Okay, and then this question is to take one of those, translate it and square it, and things get even weirder then because it's still behaving quite sharply, quite angular, almost sharp corners, but it's doing this weird like down, across, down and up thing along the way. It's maybe surprising that it'd be that complicated. The question doesn't really ever get to saying this, but the integral from 0 to 1 is about 1. It's roughly 1 because this thing is so flat that area is like a square, and the area of a square is just multiply the sides together. That's width is 1 and height is 1. The question never quite gets around to making that point, except we're going to calculate that area. It's going to turn out to be about 1. Okay, right. Which part was it that I was asked to do precisely? I think it was not this part, it was 4 that someone asked me to do in detail. Herb says in chat, the point where it quickly dips changes with n. We find where that is for each n. The quick dip is near 1 because that's where it's 0. I think that's the same for all n, that it has to hit 0 at x equals 1. But the way it's doing that for different n is a little bit different. But the x coordinates are always the same. Okay, right, time to do some integration. And I think just like the previous one, I want to multiply as a square again. So fn of x is, if I multiply it out, so then the integral from 0 to 1 of fnx dx. Let's do this one carefully. So add 1 to the power, divide by the new power. Add 1 to the power, divide by the new power. Add 1 to the power, this is x to the 0. X to the 1 divided by the new power, brilliant. Plug in 1 and 0. I'm going to be a tiny bit careful here. Not that careful. They've told you that n is a positive whole number, so nothing here is actually scary. But you should really worry about dividing by 0. It's a good thing they said positive, right? So that we didn't have a 0 down here. Okay, so if I plug in 1, I get 1 over 4n plus 1. I get minus 1 over n, I get 1. If I plug in 0, then all these powers of x become 0. So that's my answer. That's my expression for fn, the integral of fn of x. Good, okay. Let's do that inequality as well. Whoa, we're going to do a show that. So I've got some expression. So we're given the idea that 1 over 4n minus 1 minus 1 over n plus 1 is less than or equal to 1 minus a over n plus b for all positive whole number integers n bigger than or equal to 1. And we're asked basically to rearrange that. What can we see? You can see a 1 on both sides, so that's pretty good. Personal taste, I don't love having a negative thing on its own, especially on the big side. So I kind of want to move that around. I'm going to imagine adding this to both sides. I just don't like having a negative thing on its own on the big side. It just weirds me out. There's nothing wrong with it algebraically, but it just makes me feel weird. So I'm going to move this one onto the left. Also, I can see that in the final answer I'm going towards, A is on the small side of the inequality, so I've kind of put it over here anyway. And I'll move the other things onto the other side. Okay. I like to think of adding things to both sides rather than multiplying by -1, because I know that multiplying by -1 has a trick to it, and I'm going to forget the trick. So I'm imagining adding a over n plus b to both sides, adding 1 over n and subtracting 1 over 4n minus 1, and getting rid of the 1 plus on both sides. Okay, what can I see? I can see an n 4n minus 1 in the answer I'm heading towards. That's making me think multiply up. I can see an n plus b. Yeah, this is going to be good, isn't it? This is going to be good. I might simplify that thing on the right-hand side first. Before I start multiplying it up, I can see that for the final thing there is all nicely factorised into brackets. So I might try and simplify this. I've got the sum of two terms, and I want products of things. What is that upstairs? That's 4n minus 1. So if I write this all over n 4n minus 1, it's 4n minus 1 over here, take away n. Good, that's 3n minus 1, which makes me happy because there's a 3n minus 1 in the question. And then I think I can multiply up by everything, being a little bit careful to remember, once again, all those things are positive. Provided by b is bigger than -1, I guess. They're positive. It's positive in the question. There we go. A and b are given to us as positive numbers. So n plus b, n, and 4n minus 1 are all positive. Multiply it by all three, and we should get the thing in the question. I think it did. Hooray. Yeah, cross multiply. Really big, loads of cross multiply. Here's the bit that's interesting, really. I mean, we've done some inequality shuffling. With that expression on the screen there, 3n minus 1 times n plus b is bigger than or equal to a 4n minus 1n. I'm going to explain why a is less than or equal to 3/4. And here, crucially, we're going to need to remember this is supposed to be true for all n, which should make you suspicious, I think. How could something like this be true for all n? Or maybe it's easy for it to be true for all n, right? We should check some values or something. In particular, to be true for n equals 1 and n equals 2 and stuff like that. So when I put an n equals 1, that'll be 2 times n plus 1. Let's see what happens for n squared. That'll be 2 times n plus b would have to be bigger than or equal to a times 3. Okay, so that's an expression involving a's and b's. But I can see that this says something about how a has to be. I didn't plug in all of my n's. Okay. This says that a has to be less than or equal to b plus 1 times 2 over 3. Some sort of fact, right? Okay, not too bad. Not what I wanted. There's some relationship between a and b. Let's see if I can generate another one just to see what happens. I mean, it'd be really good if this was just a result of plugging in n equals 2, right? N equals 2 gives me 6 to 8 equals 5 times b plus 2. I'm going to remember to plug in the n this time. And on the right, I've got 7 times 2 is 14 times a. So this says that a has got to be smaller than 5/14 of b plus 2, which now feels like less like where I'm trying to go, because the number 14 has appeared, which I didn't really want it to. Yeah, I didn't really want a 14 right now. I wanted this 3 over 4 thing. And it feels to me like that's a more strict requirement. It's a bit tough to think about, really, because this 1's increased to a 2, but 5/14 is about a third, whereas 2/3 is a bit bigger. So it's a bit of a tougher requirement. So it kind of feels like if I make n really large, then that might be good. What have I got? On the left, I think I've got a quadratic for n, and on the right, I've got a different quadratic for n. So if I multiply out the left-hand side, oops, there we go. Minus n plus 3nb minus b has to be bigger than or equal to a times 4n squared minus 4an for all n. Let's write that out. Yeah, and it's about the long-term behaviour, the coefficient of n squared here. And maybe you've noticed that I've got a 3 on the left and I've got a 4a on the right. That's the kind of where the 3/4 is going to come from. If this is going to be true for really large values of n, then the only things that matter are the coefficients of n squared. Or said differently, if I move everything onto the right, I need this to be negative if everything's on the right. I need it to be an unhappy quadratic so that it can stay negative. A happy quadratic will always eventually be positive. That's a nice line-up, isn't it? A happy quadratic will always eventually be positive. A negative quadratic can be, a sad quadratic can be negative forever. So if I shuffle this 3 over there, I would need 4a minus 3. I would need that to be negative for this to be true all the time. Well, sort of necessary for this to be true. Once I've shuffled that around. So just minus an? Possibly. Yep, no 4 over here. Thank you. Good thing that didn't affect the next bit. Good, it's going to affect the bit afterwards though, isn't it? Thank you, chap. Okay, so it's got to be not too big. Does that make sense with the thing at the top? So n plus b at the top of the screen there. N plus b is a translation, a is a multiplication. So it's talking about how this integral is less than 1, but you can't subtract off too much, otherwise it won't be true for large n. This thing is actually getting quite close to 1 vaguely quickly. You put a bigger number for a down there, then the inequality at the top's not true anymore because the actual thing on the left is getting close to 1 faster than this minus 0.76. No. Why did I only consider n squared and not n? So this series of inequalities that I'm generating, n is 1, n is 2, it's pretty pedestrian. If I put in n is 1,000,000, then this term over here is 3 trillion or something. Wow. Minus 10 to the 6 plus 10 to the 6 is pretty big. I'm not trying to take that away. I don't really know what b is, some positive number, but is it really 3 billion large? 3 million large? I don't think so. If it is, I'm going to make n even larger. This behaviour for large values of n says that by the time you get to huge values of n itself hardly matters. N squared is where the party's at. That's just huge. In order for this to be true, you're saying that a times 4 trillion, has got to be less than or equal to 3 trillion. With some like rounding errors from these 10 to the 6s. But a times 4 trillion has got to be less than 3 trillion. It sounds like a has got to be less than 3/4 to me. And if it's the case that the a's or the b's are actually huge numbers themselves, well, just make n even bigger. So this is true for all n, including n that's twice as big as a. Sort of weird. A is fixed, n can change. The leading term is all that matters for n. Polynomial facts. There we go. Thank you, chap. Okay. Oh, we're about to hit 7 o'clock, and I need to solve for b. Let's go. So if a is equal to 3/4, then we can plug this in. The quadratic then becomes a linear function. Because it's a linear function, we still have this sort of problem though, that we have a linear function and we want it to be negative for all n. Let's see if I can rearrange it really fast. So if a is 3/4, those cancel. I get well, let's put them over here. 1 minus 3n. 1 minus 3bn. I'm moving things onto the right hand side. Minus 3/4 n, and on the right plus b over here. I move everything in. There's a linear function. Well, I want it to be negative for all positive n, all n bigger than or equal to 1. In order to do that, it needs to be negative when n is 1, and then it needs to not be going upwards. Linear functions. So it's the coefficient of n that matters for the long-term behaviour, but also, even if it's got negative gradient, kind of need to check that it started at a negative number as well. This thing on the right, in terms of n, it's got to be like this, off the bottom of the screen. There's two things to check. One, that it's got negative gradient. If it's got a positive gradient, it'll eventually become positive. And two, that it's not like this, right? That it's not positive and then ends up being negative. Yep, so when n is, if you plug in n is 1 and n very, very large, then you get two different constraints on b. One of them says, if you plug in n is 1, then you find that b b has to be bigger than or equal to 1/8, and if you plug in the kind of long-term behaviour, you find that the kind of gradient here says that b has to be bigger than or equal to 1/12. And we want both of these to be true, so we should look at b bigger than or equal to 1/8. And that's our answer for the last part. 7 o'clock came up on me very quickly there. Very suddenly we've hit 7 o'clock. So I think I've got to wrap up actually. Sorry if I finished very suddenly. Time, eh? It's probably because I did all those Desmos pictures. I haven't told you about signed area, but we'll have to save that for another day. Emmanuel in chat, let's talk quickly. Says, if you get extra time in A-levels, yes, you can apply for extra time in MAT when you register for the test. I've done that thing where I turn on chat and didn't put it on the screen. When you register for MAT, you can apply for extra time as well. The idea is that if you get extra time in normal exams, you should probably get extra time in MAT too. That sounds fair to me. Good. Okay. Bit of a more chaotic and more content kind of live stream than the last couple we've had. Next week is graphs and transformations. So I was really pleased today to see people talking about transforming graphs in order to sketch them. We're doing a bit more of that next week with some more graph transformations. There's about 2 or 3 types of transformation that we need to know about, so not a huge amount. We're doing a little bit more of those. Somebody has looked ahead on the timetable. The computer science episode 0 and 1. We're going to do some stuff about computer science to look at question 6 in particular on the MAT. Question 6 is for people who are applying for computer science or joint honours, and we're going to do a bit of a deep dive on that sort of thing. But hopefully it'll be interesting for maths people as well. But I'll be here, so I'm hoping it's interesting for me. That's not for a few weeks. Next week is graphs and transformations. Thank you, everyone. Have a nice evening. It was fun having chat on screen. It's fun doing integration with you. Right, good. Okay, how do I switch it off? Good. Oh yeah, and the next one is straight after. They've made a good point here. Straight after the open day. Someone says mine none, but after the open day, which is going to be the same for me. Going to do the open day, and then immediately go from the open day to the live stream. So that's going to be a thing. Yeah. Right. Well, wish me luck. Bye.